Okay, so this is assignment 2 of MA359, question 1, which says let K be a closed subset of the interval 0, 1. And for each n, we're going to define f of n as the union of intervals of the form m over n, m plus 1 over n, where m is in 0, 1, all the way up to n minus 1. So union of intervals of this kind that contain at least one point in K. And the first part is to show that this intersection of all of these f of n's, this f n's, is K. Okay, so we'll do this by showing the inclusion in both directions. So first suppose x is in K, then there is some m, so one of these m's, such that x is in m over n, m plus 1 over n. Okay, so why is this true? Well, you see, this is separating the interval 0, 1 into pieces of length 1 over n, right? So if we look at the interval, then we're just taking closed intervals of equal length like this, right? I mean, there should be some more in here, but they're all length 1 over n, 1 over n. It's kind of like partitioning it, but then there's some overlap because they're all closed sets. Okay, so we know this, but then this, by how we defined f of n as a union of all the intervals that contain an element in K, this is in f of n, and so we know x is in f of n. Okay, well, if it's x is in f of n, x is in f of n for every n, right? Because, okay, I didn't specify what n it was. I should have said something like given n. We should have said here given n. Then we have this. So x is in f of n for every n, so it's in the intersection. And so this means K is a subset of the intersection. So we had x in K and then x in the union, so we have inclusion this way. Okay, now let's suppose the converse, right? Let's suppose, so conversely, suppose x is in the intersection. Well, then we know that given n, x is in f of n. Well, because it's in f of n, then because it's made of the union of sets of this kind, x must be in one of those sets. So there exists m such that x is in a set of this kind, because that's what f of n is made of. Okay, well, if it's in one of these sets, because these sets are in f of n, we know that there is some element in K that's in here. Otherwise, it wouldn't have been included in f of n. Okay, so let's call that element x sub n. So there is an x sub n in K such that x sub n is in. And so what we can see now is that x sub n and x, they're both in this set of length 1 over n. So the distance between them can be at most 1 over n. So we have x is less than or equal to 1 over n. Okay, so that means the sequence xn, it converges to x. Okay, now recall that we said K is closed, right? So this sequence is actually in K because all of the elements in the sequence are in K. And so this is a sequence in K that converges, and because K is closed, it converges to an element in K, and so x is in K, and then we have the reverse inclusion. Thus, the union is a subset of K, and because we have this and we have the reverse, then we have K is equal to the intersection. So we're done. There's another part we'll do in the next video. Thanks for watching.